Yeah, and I will share my screen for you. So just a moment. So, and then here you see the topic, SINFONY, seamless combination, Nowcasting and NWP, and so on, presented mainly by Dr. Ulrich Blag. He is the chair of this big project. Here you can see the his email address, and Wilfried Jacobs is my name, and I'm at the Meteorological Training Center of the Deutscher Wetterdienst, and I will start with a few slides. But in order to give you the impression about the huge project, how huge it is, you see here a list of names, 41 people and sometimes even more. And yeah, it is really a big project running since, when I'm correct, about 4 years. And then it will continue also for several years. Yeah, because there is a lot of things to do. So my part is a repetition, a short one. So, there is it. So there is it. Maybe that some of you have probably participated in the first webinar about SINFONY. That was on the 26th of January 2021. And I will give you a brief repetition in order to set you into the context, the challenge, the principal challenge, basic ideas, aspects, but only related to the radar, because Uli Blag will mainly concentrate upon the numerical weather prediction aspect. So, therefore, here we go. So what we have presently is, yeah, you see also the challenge. On the right side, you see an animation of the measurements. Radar reflectivities are shown here. And here on the right side, that is an, yeah, more or less a linear extrapolation. It is purely deterministic, rather cheap because it's running very, very fast. And so you have it every 5 minutes. But it is not perfect, as you can see, for example, here, this area, and here, and you compare this here, more or less wrong. Yeah, that means that is not sufficient. It is a first guess for the forecaster, but it's not very useful for nowcasting. Therefore, we need something more. And the next step, what we did already at the DWD, Deutscher Wetterdienst, is that we have a mesoscale model, or Cosmo DE is the name, or now presently Icon D2. That means it has a horizontal resolution of about 2 kilometers. And it is also possible to simulate summer convection, with the exception of small-scale convection. So there is a step forward, but when you compare the left image here with the right one, you see also big differences. But what is in principle included by modeling is that we have development included, and it is better than only extrapolation. But you see also the big errors, for example, here on the side, yeah, that has nothing to do, or a little bit with the reality. But here that is a little bit better. So we'll have an impression, rough impression about the development, but not more. And that is a big challenge, and one of the main tasks of SINFONY, that now presently we have a separation between radar-based forecasting and numerical weather prediction based. And so they are generated separately without any connection to each other. And so we do not have a smooth transition from the radar domain to the domain of the numerical weather prediction models. That is one of the big challenges of SINFONY. You see here on the right side the principal problem. On the left part of this image, so have more or less the nowcasting domain linear extrapolation, more or less here in our radar warning app of smartphones of DWD. and you have here a nowcasting starting point 1315 to 1515, and here the blue line in between, yeah, that is so the transition to the domain of the numerical weather prediction, starting time 12 UTC, and the forecast for the same time as on the left part of the image. And you see here as marked Prenzlau near Berlin or Eberswalde. So here the numerical model gives some reflectivity and precipitation, sorry, and here just a little bit west of it, nothing. So that is a big problem what has to be solved. So ideal concept of the symphony, maybe that some of you has already seen this diagram. Here you have the forecast time, more or less long, and here the ordinate shows the verification score. 1 is more or less perfect, 0 is more or less useless. So the nowcasting is one branch. It's beginning very reliable, very good, but there is a very fast decaying quality or decreasing quality, and after a few hours you will have more or less no benefit from it. So the numerical weather prediction compared to that, and you see at the beginning nowcasting is better, but when the forecast time it becomes longer, then the numerical model is better, but not good, of course. Yeah. So, and then we have first the possibility to improve the nowcasting forecasting technique, and then we will get some better results. And so you have here on the right part what is presently done. We have field distribution on grid, and so for example precipitation within 1 hour in form of reflectivity also. You can have such images, and we have cell objects with some attributes, for example a maximum DBZ value, maybe gusts, is there hail included, and so things. So typical characteristics of some cells, and they are presently more or less extrapolated linearly. So improving methods, maybe we have better extension, extrapolation, and maybe also additional techniques, maybe some statistical help, for example also ensembles that cover some uncertainties. The method itself, you can also improve the interpolation, extrapolation method, for example. You can also remove some very small scale convective cells because they are not predictable. That means you should remove them because they are more or less producing noise, and so you will not have much benefit for the forecaster. And also ideas to include the tendencies of cells and growing independent and a decaying of an individual cell in a dependency of the forecast time or a cell age. Pardon. So that is also possible to include, and that can be based upon climatology, for example, for Germany or also other countries. So forecast is the other branch, and what is almost realized is that we have more forecast starts every hour for forecast length 12 hours. A rapid uptick cycle is the meaning of the abbreviation. Then we have also a higher resolution, 1 kilometer, and better model physics. So that is a possibility what we can use, but also that is very important to have the best possible data at the beginning. Presently, we have a precipitation scan of reflectivities included. And what is a big advantage would be to have volume scan radar available, and also in addition radial wind components, and to assimilate that to the model is not so easy as it might sound. It isn't very big and challenge to realize it because the model is not able to understand, for example, the language reflectivity, then the needs, for example, latent heat, nudging or so. Yeah. So then Meteosat is not yet included, but first tests are in progress to include at least a visible channel. IR has still to be done, and very important, lightning. That isn't direct information. Is there light? Is there thunderstorm going on? But very difficult to include this information so that the model is able to proceed with that, to calculate it, to include it into the forecast equations. So then we have the combined product, radar and numerical weather prediction, and very important is the verification, RMS, median, distance error of cells, for example, and then the object shell, for example, to verify is the cell intensity okay, is a hail size okay, and so on. That is the so-called attributes. So now, ensemble forecasting is a very important part, and here you see an example of 3 different members: number 10, number 20, number 30, and you see more or less similar, but different in detail. So that is done 40 times. It depends in the calculation time what is possible to realize. And so that is the first step what we are still using in Deutscher Wetterdienst. So, and you would be to include uncertainties, because here, for example, here's very small scale cells are very difficult to forecast. So you should remove that. They're all confusing the forecaster. So, and here on the right side, that is partly almost done. Here the first 2 rows, Conrad in 3-dimensional, so a volume scan, and that is presently in development, in test phase. And what is done is here to have ensemble forecast. For example, here the red parts is the Conrad 3D, the ensembles. Sorry, it's a little bit covered. And here the blue ones are the analysis for verification. So, and old we had deterministic and linear extrapolation, but new growing decaying of the cells. That means first that you have in climatology growing and decaying of cells of different scale, and also Kalman filter, for example, in order to learn for the past and to correct the forecast accordingly. So that is a fast repetition, and now I will hand over to Uli, and thank you for listening.
So, can you hear me?
Yes, we can.
Okay.
Loud and clear.
Is it loud enough?
Yes.
Okay, perfect. So I have to find. So just a second, I have to, there are the slides. So can you see the slides now?
Yes.
Okay, perfect. So let me just introduce shortly myself. My name is Ulrich Blahak. You can call me Uli. I'm a meteorologist. I graduated in 2000 from KIT, and now I'm a senior researcher at Deutscher Wetterdienst. My research interests are radar meteorology, cloud microphysics, NWP models, and nowcasting, and this qualified me to be now the project leader of this big SINFONY project. You need all these components in that. You have seen that. But my interest and love for the meteorology, it comes from gliding. So as you can see here in a club ship in France, and that is the practical connection to my theoretical and daily work, so I can verify on the spot. And from time to time you see rare things like this spectacular lenticular cloud, which spanned from had a base of 3,000 meters and went over more than 8,000 meter, which I was able to use the wave lift, which is connected with it. And then you see a happy pilot in 6,000 meters. Of course, with oxygen, you can see that, but that's my background. And now I switch to the professional matters. So today's part of the SINFONY series of lectures is part 2. It's about the numerical model. And I'll show you today what we are developing to improve the data assimilation and the model physics for this very short range forecasting of up to 12 hours. And we target explicitly convective cells in the summertime, which are during this time of the year the most challenge. And I start with showing you what we are currently running operationally. So that is not what we develop in SINFONY. That is what we already have. We have a global model. It's ICON. It's our ensemble system and a deterministic member. In the global model, we have a so-called ICON EU nest over Europe. It has a resolution of 6.5 kilometers in the deterministic version and 20 kilometers in the ensemble version. And nested in that, we have a ICON 2-kilometer resolution nest. We call it ICON LAM D2. LAM stands for Limited Area Model version of ICON. And it gets its initial and boundary conditions from the ICON EU. And we generate forecasts over the Central European domain for every new forecast every 3 hours and up to plus 48 hours. That is our standard operational suite nowadays. What we want to do in SINFONY is we want to add a second instance of this ICON LAM D2. We call it SINFONY Rapid Update Cycle. The rapid update cycle means that we generate new forecasts every hour instead of every 3 hours. And because that is more expensive, we don't forecast as long. We just forecast 12 hours. What we also do is we look at a 1-kilometer nest, which is inside this domain again. But so far, it's not so promising. I'll show you in the talk that we invest for now our computing capacities into better microphysics instead of resolution. That was one of the outcomes. So the initial conditions come also from the boundary conditions come also from the ICON EU, same as with the other ICON D2 model. But the initial conditions we add additional data sources to it. Wilfried mentioned that already. We add 3D volume radar, we add the visible channel of the Severi satellite, and we add some lightning information, but that's more in the future. And with the new forecast every hour, we combine with Nowcasting forecast to have one seamless product or film or movie for certain weather elements. And with this combined products, we first concentrate on precipitation and cell objects. I'll show you that later. So, and the big challenge is if you forecast rapidly, you also want to complete your forecast very rapidly, otherwise it's useless. So we want to have the rapid update cycle available 45 minutes after the actual date, and that's a big challenge. Our current model needs more than double time. So, some characteristics and challenges of the model. 4 years ago, we started out with our old Cosmo model. So some of you might have heard the name. And in the meantime, we moved to ICON limited area mode, which is this new model. What we have done is we adapted the model configuration in both models, and in ICON LAM it's work in progress. We have the same model domain and the same grid as the 3-hourly ICON LAM D2, and we start out with a grid spacing of 2 kilometers. Our rapid update cycle, it has a slightly different optimization of the data assimilation and the model forecast itself, and we aggressively optimize for the first 6 to 12 hours forecast lead time. So that's the main difference to the standard model. We also do more frequent output, of course. If you are concerned with convective cells, 1 hour rain sum doesn't tell you much, so we do much higher output frequencies, which is also a challenge and also a challenge to the user in the end. So we output the 3D model fields not hourly, but with every 15 minutes, which is a higher frequency. Additionally, we generate, and I'll show you that in a minute, we generate synthetic radar volume scans of all German radar stations every 5 minutes. And these synthetic scans from the model can be directly compared or combined with the observed radar scans. What you can do with this is, for example, you can feed these simulated reflectivity volume scans. They look exactly like observations. From a technical point, you can feed that into radar algorithms, which we run, and you can do the same radar composites as in the observations. You can also do a Conrad 3D cell object detection. That was what you saw on this last slide of Wilfried on the right-hand side. These were objects from observations, but you can do the same with synthetic radar scans, and so you have simulated convective cell objects. Yeah, what were the problems on our, until last year we had an old HPC, it was a Cray computer, and compared to the demands of the rapid update cycle, the resources were very limited. So we had the problem of slow and cumbersome experimentation with the old machine. Now we have a new HPC installed, and it's currently constantly upgraded. It's a NEC SX Aurora system. And only now the situation becomes better for experimentation. That's why we could have the Cosmo model for the old in previous years only for test periods from the past. So we had two or three golden months which we worked on all the time. But with the Icon LAM, since recently we have a daily test runs for the actual weather since beginning of May. So that's the first time we actually run something on daily weather, but it's only mainly for technical purposes and for checking. It's not presented to the forecasters yet. Yeah, and I briefly mentioned it already. The other challenge is we want to present the model results more in observation space, which is not common at our forecasting center. We have all these synthetic radar reflectivities. We generate also synthetic satellite observations. And why not present the model results for these high resolution runs and in a rapid update cycle in this metric to the forecaster? Because as a forecaster, you are used to looking at a radar picture or a satellite picture, right? And that's what we want to do. And this to generate synthetic observations, you need so-called forward operators in the model that transform the model state variables, which are temperature, pressure, wind speed, and hydrometeor contents, into something that looks like a synthetic measurement. So there's some physics of the measurement process involved, and you call that forward operator to generate synthetic satellite picture or synthetic objects or synthetic radar pictures. Yeah, and what you can do with that, once you have these synthetic observations, you can also combine it with real observations and forecasts of real quantities from Nowcasting to end up with these seamless combined products. And that will be not the talk of today, that will be the third part of the series in fall. So, and then you can also do with these simulated observations, you can do a very direct comparison or verification of observations and model. That's what we do, and in the pilot project, in all these synthetic measurements, we concentrate on reflectivity, on cell objects, also on precipitation rate and sun for the combined products, of course, and the visible channel of severity during the day. And not the least, this forward operators enable to assimilate these data sources finally in the model, in the initial state. That's done at DWD in our system, which is called localized ensemble transform Kalman filter. Yeah, what we learned during the years is that our standard cloud microphysics, it's a so-called one-moment scheme, and I come to that point in a minute, is not good in giving relevant cloud information that could be transferred into good synthetic observations. The cloud information is not good enough. So we experimented with a more expensive, so-called two-moment cloud microphysical scheme. That's more modern, but also more expensive, and we need that for good synthetic observations. Yeah. So this two-moment scheme, we need that because to have good precipitation and simulated reflectivity at the same time, is a big challenge for bulk cloud microphysics schemes. So as you probably know, a one-moment scheme would forecast only one water content or ice water content from different hydrometeor classes. And this one information, this one piece of information is not good enough to estimate the relevant particle size distribution. So how many small or big particles are in the volume for these simulated synthetic observations. What a two-moment scheme does, so for example, our standard one-moment bulk scheme that you can see on these two pictures comparing observation and operational one-moment scheme is not able to simulate high reflectivity cores and convective cores. So these 60 dBc in the cores are missing in the microphysics, and that's a systematic error. And this is much better with the two-moment scheme, because what is a two-moment scheme? First, our two-moment scheme adds an additional source of big particles. It's a Hale class additional to the others, Graupel. And what makes it expensive is it adds a second moment of the size distribution, not the number concentration, additional to the mass densities of all these hydrometeor species to the prognostic variables. And when you have two pieces of information, mass content and number content, you can estimate the particle size distribution in a much more realistic way to end up with, for example, places where you can have really big particles and making high reflectivities. So this is good for data assimilation because it has less bias, and it's good also if we want to run a cell detection algorithm on these synthetic radar volume scans to detect Conrad 3D cells, of course. Yeah, here is an example. I hope the movie runs halfway smooth. On the upper part, it's a vertical cross-section through an intense Hale cell. And on the upper part, it's a one-moment microphysics where you don't see a convective core, where in the two-moment physics, it's much better. That is from a paper we published in 2017, a case study. And in the observations, you can see in this max copy on the upper part, the vertical cross-section that really, compared to observations, the two-moment microphysics is more realistic. Yeah, by the way, this comes from this particular storm. Nice picture of a brutal Hale cell. It was in 2013, 28th of July. And together with another cell in northern Germany, this event was the most expensive, I think, disaster worldwide in terms of insured losses. It was a 3 billion euro loss because this Hale cell, it moved, you can see, it produced 10, 15 centimeter hail, and it moved, you can see the track here, it moved in an area south of Stuttgart. Stuttgart, you know, Mercedes-Benz. A lot of people are wealthy there, and they have these big cars and good houses, and this hail crashed many things, and so the loss was big. Even I think we didn't have much personal injuries, but which was lucky considering this hail, but it was an expensive event. Yeah, what is now what we are doing now in SINFONY for the ICON LAM? Our task is to make the two-moment cloud microphysical scheme fit for operational application in a SINFONY rapid update cycle. Because the standard model uses a different microphysics scheme. Additional, we look at the 1 kilometer nest simulation. Then we also care for the high resolution planetary boundary layer. We have a new stochastic PBL scheme in ICON, replacing the current shallow convection parameterization. Then we look also at new object verification methods to complement the standard methods, of course. Cell object properties, visible and infrared satellites, and so on. So now SINFONY data assimilation in a nutshell. I switch now from model physics to our data assimilation parts. First, we care for the assimilation of the severe visible channel during the day. You can see here a simulated scene from the model. Then we also assimilate now 3D volume scans of radar data. So these elevation sweeps are all assimilated in terms of radial wind and reflectivity. I will also show you later that we add, for a certain reason, the lowest elevation during a so-called first guess run, where we apply the traditional latent heat nudging method, which is beneficial to combine it with the LATKF. Yeah, something which is more difficult than radar. Radar is difficult as well, is difficult, but lightning is more difficult. You can see here two scenes of an observed lightning flash density and the first guess from the model, which is based on a forward operator. It's called lightning potential index. And you can see this really spotty behavior, and these types of data are really hard to assimilate in any data assimilation scheme because you have a lot of nulls and some spots where there is something, but that's really difficult, and I'll show you later why. Yeah, and alternative or additional to all these things, we also want to concentrate more on convective cells, and so we dare to assimilate the really 3D objects detected from these volume scans. And on the lower right part, you can see an example of such an object. It's encircled, it's a high reflectivity region encircled by a polygon in red. And what we would assimilate is just the information which is in the object, and we would neglect all reflectivity information outside of the object, but this reflectivity information is already contained in our normal 3D radar reflectivity, which would be assimilated at the same time. So, and now we developed this radar reflectivity very far in SINFONY, and the normal people from the other department thought, okay, that's good enough, so we also make it operationally in our normal icon D2. So now we have the situation, what we developed is operational now, and we have to follow with our SINFONY rapid update cycle. A similar story for the Severi Vis, it's very far developed. And now we want to make it first operational into our normal icon D2 and then in SINFONY rapid update cycle. So, and the lower part, the lightning assimilation and the convective cell objects, this is work in progress. Yeah, short sketch of an object and how we assimilate it. So, picture this might be your object. There is reflectivity everywhere, but we detected this object. And what you can do with an object, you can assign it a central point. That's the point of reference. And then it can have different properties which you can assimilate as a bulk information. That could be, of course, the location. That could be the area of the object. That could be the wheel, vertical integrated liquid, cell-based. That could be the mean reflectivity, or that would be reflectivity max. That could be a height, so echo top, echo bottom, minus echo bottom. Yeah, and you can assimilate that if you have an observed cell or observed cells around it, which you can also assign these properties. And then, for example, it's possible we found a way to also to also include the spatial shift of cells as a quality measurement, so that in this case we would not say it's a really bad forecast. We would say, okay, the cell is there, but there is some spatial distance, but it's not too big, so that's not so bad. So we would punish, or we would rate the distance of the cell also, and this is something which you can do with objects and not with the other things. So how can I erase the screen? Okay. No, just I go to the next slide. Sorry, it's new. This new technique is new for me. Yeah. So coming back to simulated satellite pictures. and a bit more detail, which we are using for data assimilation. You can see here 3 different versions. One is the observation, and then in the middle is the representation with a 1-moment cloud microphysics scheme from an older case. And on the right-hand side is the same model with a 2-moment microphysics, and you can already see that both models are certainly wrong in a certain way, but they are much different, and the cloud microphysics is responsible for that difference. And now our task is to tune the 2-moment cloud microphysics also in a way that it makes good satellite observations. And the forward operator which we are using to produce these images, that's a new thing. It's a fast operator for visible spectral range, which was provided by University of Munich. It's called emphasis, and it's the fastest operator in the world. Visible is really difficult scattering theory, so these simplifications and approximations which were made here are very good, and so we are happy to have this. The problem is a bit that these data itself, the reflectance data in the visible, they don't tell you something about the height of the clouds. They just you just look at the clouds from above, and you don't really know at which height they are. And that's a bit a problem in verification, but also in the data assimilation, particularly in the data assimilation, which we have to cope with. Yeah, the other high-resolution data are radar from our network. For this, we have a forward operator called MVORADO, the efficient modular volume scan radar operator. It does simulate along each radar bin, each radar array through the model domain. The model grid points are depicted in green, and the radar array measurement geometry pulse volume is depicted in black. So we can simulate along each ray of a synthetic volume scanner, radar reflectivity, radial wind, and also currently under development new dual polarization parameters like ZDR, phi-dp for the experts of you. The others, it's not important for now. But the important thing is we can do it for entire volume scans live in the model run. So we don't need to store big amounts of data to do it. We just do it every 5 minutes within the model run. And we can do it for the entire radar network, here the German radar network. And this is a forward operator which can produce 5-minute data of simulations without much affecting the runtime of the model. That's a big success, I would say. Yeah, and it produces, in our case, 16 stations of this type of data, which can be then further processed. And you already saw that in the light of combining model results with radar data, nowcasting data, this could be very important. And so just to show you one example what you can do with it, we feed the simulated volume scans into the same Polara algorithm that produces the observed composites, for example. You can do that with the model data itself, and then you really have the same measuring geometry behind it. You have implicitly simulated scan geometry errors of the radar, and you can really compare that one by one. And that, looking at the pictures, does tell you a lot about what's going wrong in the model, what's good, and what to do. And it's a fair verification, and it's also a good source for data assimilation. Yeah, brings me to data assimilation. I told you that we are applying a so-called local ensemble transform Kalman filter, LETKF, at the kilometer scale. And how does it work? Just in a nutshell. Consider we have an analysis from time -1 hour. It's an ensemble of analyzed model states from which we can start a short forecast, in our case 1 hour. This is called first guess forecast. So it's a 1-hour forecast where some errors in the model have built up, and now we want to correct these errors with observations. And for our purpose in SYNFONY, we particularly add radar, satellite, and lightning information with a so-called forward operator H of this first guess. So model states are converted to observations in each member, and then feed into the black box called localized ensemble transform Kalman filter, which optimizes this. And the outcome is a new corrected ensemble from which you can start, for example, a forecast for the 12 hours, or you can repeat this cycle with the next small hour forecast and do the next data assimilation after 1 hour and start a new forecast. That's what we're doing. So this H is the forward operator applied to the model state. And then basically the LTKF, you can view this black box as basically 2 steps, simplified. First, the LTKF corrects the ensemble mean towards the observations. And in a second step, it tries to rebuild around this new corrected mean, a new ensemble centered around this mean with about the same spread. And it does this by an optimal linear combination of all the first guess members. Linear combination is just the weight times member plus another weight times another member and so on. Weights add up to 1, and this gives a new first guess ensemble. So, and we do these steps independently for each model grid box. That's a necessity due to be able to finish that in reasonable time on a parallel computer. And we do also, to limit the computing amount and also the physical content, we do a localization in observation space. So for each grid point, we only consider all observations within a certain radius. For radar, for example, this radius is 10 kilometers or 15 kilometers only. Yeah, I skipped this sketch of an ensemble DA cycle. What I want to show you, where are the difficulties? So you probably have seen, you remember this score plot, which we always show. So where this is forecast time, and this is a score. And I define a score that is good for if it's 1 and it's bad if it's 0. And if you now start to do data assimilation at T0 and do a forecast, then usually when we don't assimilate radar and this high resolution information, we would get something like this, an analysis with a score here, and then the model score goes down over forecast lead time. So in a second step, if we do a bit of data assimilation, so we can configure the data assimilation with different error informations on the observation and on the model. And based on this error information from the model, for example, comes from the ensemble. You can compute standard deviation at points. This is the model error. And for the observation part, we also need an observation error. This is a tuning knob. And if we play around with the tuning knob and we specify a very large error for observations, that means we don't trust it very much, then we would get some impact, but not so dramatic in the beginning. And then the model would go down like this. Okay. Then if we turn the observation error down, we get more impact. Then we might end up like this. So unfortunately, this doesn't go on forever, because when we do it too much, so we bring the analysis very close to the observations, something like this happens usually. So that's not good. And why is that? You have to remember that each assimilation step introduces a bit of unbalanced model states. I mean, here we observe radar reflectivity. Radar reflectivity is directly connected to hydrometers. Okay, the ensemble Kalman filter learns if I want to have more reflectivity, I have to put in hydrometers. Fine. So, but what happens is the hydrometers in the ensemble are correlated to wind speed, and temperature and moisture in a certain way, which is dictated by the ensemble. And this correlation is linear. It does not know nothing about model physics or model processes. It just does anything with the background state, and you get noise in the balances of pressure and wind speed and temperature. And the more you draw to the observations, the larger this noise is. And at some point in the story, the noise is so big that you generate so many gravity waves when the model starts that these gravity waves start to have an influence on the forecast far away, and they destroy the quality elsewhere. And that's where the score goes down. And the task of data assimilation tuning in practice is to find the sweet spot where this is a maximum, where you can get a maximum in the score without doing it too much and losing too much quality later on. And that's why it's so difficult. Yeah, so an example, just to show you as an example how we do assimilate this data, this radar data, on the example of radial winds. The first step is not to assume all these high resolution kilometer, 1 degree pixels of radial wind, but we reduce the information content to so-called super observations, averages in 10 by 10 kilometer grid boxes depicted here in the center. And this is done with the observations and the synthetic radial wind, and then the differences at these points are assimilated. Yeah, I skipped the next. We do the same also with 3D reflectivities, and they are assimilated in a similar way. And also the severe vis data, same story, super observations on a 10 by 10 kilometer grid and assimilating the differences. We also have a publication of the radar thing. Yeah, what are further aspects of improving the reflectivity DA? One thing I didn't mention is that our system, or in fact any data assimilation system in an ensemble sense, it has problems when we have no spread in the ensemble. For example, all members could have 0 reflectivity at a certain location, but we have an observed cell here. So in that case, our model thinks the ensemble has spread 0, so no error, so it's perfect. And in that case, nothing is assimilated. And so what we have to do is, during this first, or what we could do is, what we in fact do is, we have to introduce some spread by some measures. And one way is to use this first guess 1 hour forecast to generate spread in regions where we need it. And you can do that by our traditional latent heat nudging method, which continuously learns from every 5-minute precipitation scan. Where we miss precipitation, we introduce heat and moisture to generate updrafts, lift, and precipitation later on in a continuous and relatively weak way. But the other thing is, that's the one thing we are doing, and that's very successful. We have also a technique which is, but it's experimental, but it's cool, I think. We do, based on our internal radar data, which we have in the model, we have the observations in a and the simulations, and then we compare internally during the model run every 15 minutes where is a missing cell. So on the left-hand side, you can see an observation example. On the right-hand side, you can see 2 spots where this particular model member misses an isolated intent cell. And when we have this situation, we put in a so-called warm bubble at the boundary layer, a big chunk of warm air, which rises then up. You can see here the cloud building up, and then later on forms a realistic cloud. So this forces convection at these 2 measures force precipitation and convection where we need it, so that the next data assimilation step has some spread there and can assimilate the data better. Yeah, now how to verify convective precipitation. As you all know, if this is an observation and this is a model simulated cell, there are different views on the quality of this example. A forecaster would probably say, well, it's pretty bad because the location is a bit off. Me as a modeler would say, well, it's pretty good. What do you expect? It's nearly a hit. But in our standard scores, this is really rated bad because, yeah, the double penalty problem is imminent. You might have heard of this. And that's just what I told you. While to me as a human, as a modeler, this is a good forecast. The RMS, the root mean square error, for example, suffers from that errors are counted double because of this spatial shift. So you can picture that the root mean square error is just the sum of the squared differences over all the points in this structure. And now that the points within the observed cell, they get a big difference to the 0 in the background, and the points within the simulated cell, which is far off, get about the same amount of error contribution again, so double penalty problem. So because we want to be a little bit more relaxed against those errors, we need verification methods which are graceful to certain spatial displacements, and this is called spatial verification. Okay. Now, as an example, there are tons of scores, different scores for spatial verification, but I show you one particular, the fraction skill score, as an example, so that you get the concept. So what we do is the fraction skill score rates the relative frequency of threshold exceedances, as is a threshold, in a certain neighborhood around points. That is what we call scale. And this is then immune against small spatial displacements of patterns below that scale. So how we do it? First, you need the forecast and the observed values on the same grid. It's a gridded method. Then you apply the threshold to each field. So left-hand side, binary observation. Right-hand side, binary simulation. The binary values are 0, where the threshold is, where the value is lower than the threshold, and 1, where the value is higher than the threshold. Okay, that's step 1. Step 2 is then you decide for a scale which you are interested in. That could be this red grid box. And then you scan within that grid box point by point through the field. And for every location of this box, you calculate something, and that is the box counts. So for each box, you calculate how many pixels are above the threshold. And in this example, on the left-hand side, we would see 6 pixels in the observation are above the threshold. So the fraction is 6 by 25. On the right-hand side, similar in the observation, the pixels, there are also 6 pixels above the threshold, but their location is slightly different, but we are not interested in this small error, so they get the same score. And you do this by all the fields, then you get a smoothed picture of fractions, and then you compute over all these smoothed points this fraction skill score. That's just a relative RMS, you could call it. It's a quadratic difference weighted by appropriately. Yeah, and then for each grid box, as I said, you repeat the steps 2 to 5 for different thresholds and different box sizes. And then you get a picture for small scales and for large scales. And usually the scores are better the larger the scale, that's clear. Yeah, and with this fraction skill score, you remember probably our sketch from the beginning where we try to explain the principle of SINFONY. When we did this with our last and best Cosmo model experiment before we switched to IconLum, we got the following picture, also comparing with Nowcasting. You see here in the upper row two box sizes. So the scale is 1 kilometer here. It's very, very high resolution. It's below the model resolution, actually. It's very unfair to the model. On the right-hand side, we have 33 kilometers. And for the upper two plots are for 25 dBc threshold exceedance and the lower for 46 dBc, which is a higher threshold. And what we compare is, on one hand side, the Nowcasting, that's the blue curve, and two model versions. That one model is the Cosmo, our old Cosmo DE model, 3 kilometer resolution with one moment scheme, standard configuration with the black curve. And the red curve is the same Cosmo DE model, but with 3D radar assimilation and 2-moment cloud microphysics. And there you can see also the gain you get from the 2-moment scheme. So the scores in this deterministic verification are higher over all forecast lead times. And you start to get some skill also for this very high threshold, but it's not perfect. But if you look at the ensemble, and what we picture here is that in that example, we assume that the NWP is at least 45 minutes older. So that would be the view of a customer. Now, if you slightly modify this fraction skill score to include all the ensemble members, it's called neighborhood ensemble probability. You can picture a bit the added value of the ensemble, which a user would have. And you can already see that. Let's look at the Nowcasting ensemble in the upper part at the very 1 kilometer scale. There, the ensemble brings an added value, and also in the model at that scale. But for the model, it's more important are the larger box sizes, and there you can clearly see an improved score through the ensemble information. And then you start really for the 46 dB set to get something which is halfway usable for the 33 kilometers. And that's our important result. And now maybe to wrap up, why did we switch to IconLum then? Well, it's a newer model, and I show you here a scorecard, standard scorecard comparing 2 meter values of temperature, humidity, wind speed, radiation, and all these parameters. What you can actually see is that the root mean square error reduction, that is the green color, if the green color signifies that the IconLum is better than the Cosmo, and it's really more than, for some parameters, more than 10% reduction of RMSE in the IconLum. So that's really a dramatic impact of the new model. yeah, so we use it because we have a better forecast quality as measured by almost all standard scores. The model is more efficient on parallel computer architectures in the future. It runs half runtime of Cosmo. What I did not show is that the precipitation is only slightly better than in Cosmo, but the whole package is it. You have to know that we optimized Cosmo in the past heavily towards good precipitation. So we sacrificed other scores for precipitation, and we don't have to do this with Icon. Yeah, and now we have to also in this new Icon model, we had to stepwise adapt our SINFONY developments. Our first step was looking at precipitation with the one-moment scheme. So looking at precipitation with different types of radar assimilation with a one-moment scheme, doing step by step. So we were happy with that. The next thing is we looked at assimilation of severe vis, visible channel, also with the one-moment scheme, the next step, for 3 different months. And we were also very happy because the colors were really green for severe vis in the standard scores. If we look with severe vis at the precipitation for different thresholds and also fraction skill scores, the red curve is the with severe assimilation. We were also happy. But now what's about reflectivity forecasting? You can see that our runs with Icon, we can also run it with the standard one-moment scheme from Cosmo and with the two-moment scheme on the left-hand side. And same story as in Cosmo, with the one-moment scheme, you don't get the convective cores. With the two-moment scheme, you get it better, and that's, of course, better for all we want to do in SINFONY. But there's a big but. So we know that we also need the two-moment scheme in Icon. However, the rest of the model, many things in that rest of the Icon LAM are really tuned to the one-moment scheme. One-moment scheme has some cloud biases, so it has some properties which introduce biases in the radiation balance, so incoming radiation, outgoing radiation. And these biases have to be compensated, for example, by the soil parameterization or by turbulence, by any other thing. In the end, you get a package that is compensating errors, and that's working reasonably well. And if you take out one of the errors, namely the one-moment scheme, things get worse. And at first, so the problem to solve is we have to achieve a similar quality of other variables than reflectivity with the two-moment scheme, which is a ongoing work and a difficult task, and we are in the middle of that. We also have to adapt the model physics, of course. That's our current step 3. Then we are beginning with to adapt also the parameters of the radar data assimilation, the visible assimilation, and of the cell objects, and that's ongoing work. So brings me to the question: how good is the model representing cell properties, such a model? And what we did is statistics of these Conrad 3D cells detected from synthetic radar pictures with different models. And we started with the Cosmo model in blue and 2 versions of the Icon model with one-moment scheme, and the red curve is the Icon model with a two-moment scheme. And what you can see is that compared to the black curve, that is the distribution of cell properties from the observations, the red curve is always the nearest one. So we compare here the vertically integrated liquid of a cell, we compare ecotop 35 dBc, and we compare the maximum intensity, where you really can see that only with the two-moment scheme, with the red curve, you really get the observed high reflectivities in the cores and good objects. Yeah. Then I skipped this slide. This just shows you that we go a bit deeper into object verification and compare other properties of objects like severity or the volume or the mass or the cell speed. Always the two-moment scheme here in blue wins. Yeah. But now to wrap up, what is again the gain by a rapid update cycle? So as for you as a forecaster, it's a bit difficult to picture, but I tried. Sorry. Consider we have a time of day, not the forecast lead time, but a time of day. Maybe this might be 6 UTC, this might be 12, 15, 18. And now you put yourself in the position you have to, at DWD, you would have to do a forecast at, say, yeah, black color, at 1250, like this. So what you have so this is forecast quantity X. Could be precipitation or anything. Now you have for the precipitation, you have the nowcasting, which goes down really rapidly in that compressed frame of time. And if you want to forecast something for a later time and you want to use a model, the newest model which you could have at the moment from our standard suite is the 9 UTC run. And it might look like this. Okay. And so that would be your best you could do with the envelope of both. Now with the SINFONY rapid update cycle, you would be able to use a newer model, namely the 12 UTC model. And that could look like this. So for your forecasting, this would be the gain which you get from a rapid update cycle. And that's not bad, I would say. That's why we are investing in this. Now, just to give you an appetizer as the last slide for what you can do with all these model ensembles. It's a wealth of data. You will, as a user, you could never look at these or analyze these in due time yourself. So you need urgently what we call information compressed, condensed, combined products. And just what we do with, for example, with the model members, is we analyze for each members, we analyze convective cells. So on the left-hand side, in the upper part, you can see observed, few observed convective cells. That is just these black points. So it was a day with isolated convection. On the right-hand side, you see a paintball plot of all the model members. So different members have different colors, and the cells from these members where they come from. So you see much too a broader picture of area where the model ensemble thinks there could be cells. So what we are doing is we are clustering all these cells with a two-stage clustering process to end up with something we call reasonable cell selection or reasonable cell selection on the right-hand lower part. Here you can see, as an example, 3 clusters. The green is good compared to the observed cell. The red is medium and the blue is worst. So we would only select the green cluster based on cell properties and location. And we would say these are good candidates to use for forecasting, but then you can still see location error. And what we then do is, because location error is really hard to compensate completely in the model, we do an ad hoc position correction. So each of these cells, the green points, has a location at the observation time and a forecast trajectory. And what we are doing, we shift the initial point together with the forecast trajectory so that in the observation time, they start at the observed spot. And that is a pragmatic correction for positions. And then that is our cell ensemble for an observed cell. And then you can do further processing steps. And what we do with that in terms of combining that with the Conrad 3D nowcasting cells, that will be presented in the next SINFONY session, together with many other precipitation-related combined products. Yeah. That's a big challenge to do it in real time, but I'm sure the outcome would be very useful to any forecaster. And to wrap up, that's an appetizer for next the combined products for autumn. To wrap up, we are doing this not alone. We have a lot of university cooperations. Here you can see a brief list. We are also part of the this year's European Severe ESSL testbed, Severe Storms Laboratory testbed, which is currently running, and we have a website. And yeah, with that, thank you, and I'm open to questions.
Thank you for the presentation. And if you have any questions, you can raise a hand or post them in the chat. I can unmute you so you can talk yourself. I don't think we have had any question yet. So Let's give them a minute.
Yeah, it's a lot of information and very complex.
There is a question in the chat from Michaela. You can open the chat in the top menu.
Oops. Yeah, probably you could read the question.
In the two-moment product, some reflectivities were overestimated, especially in the southern part. What could be the cause? Sometimes this can be as bad as the underestimated ones.
To which slide do you refer?
Two-moment product. I'm just reading the chat.
Yeah. Probably this one. I mean, to say that for these simulations they are without. That's for testing without any data assimilation. That's a free, few days long forecast, which gets the same boundary conditions at the boundary. That determines the similarity and the weather pattern of it. In that simulation, yes. So we look at statistics of these radar pictures as function of height. It's called CFATs, and we see that yes, sometimes it's overestimated, but the distribution of reflectivity with height and reflectivity value has less bias in the two-moment scheme than in the one-moment scheme. Of course, from case to case, that could be different, but over statistics over many days shows that the two-moment scheme has less bias than the one-moment scheme. And in the one-moment scheme, typically we don't see any reflectivity cause ever. So you can't forecast objects with a one-moment scheme which are analyzing reflectivity cause, and that's more useful in the two-moment scheme. But of course, yes, there could be overestimations from time to time.
And a follow-up. How long after introducing observation data to the model returns the balance state, the green line you drew?
Is this referring to how long it takes to complete a forecast? We plan to have a forecast ready after 45 minutes after the actual date. So that is about a factor of 2 faster than we have now with our other model. 45 minutes after the date, we want to have the forecast and the products ready, so that the forecasters can see something on the screen.
I hope that answers.
Now I found the chat, sorry.
Yes.
How long after introducing observation data the model returns to the balanced state? Yes. When you look at that, you find typical in our sweet spot, which we found it's about 15 minutes. So if you do data assimilation and have an analysis with unbalanced state, and then you start the model, it takes about 15 minutes to get rid of all these sound waves and gravity waves it produces. Yeah.
I am not seeing any other questions or raised hands.
Yes, another question is if we try a 3-moment microphysics for predicting reflectivity, and how much more expensive it will be. The answer is no. So 3-moment microphysics would add another 30% runtime because you need a third moment for each hydrometeor category. But the benefits which we see from literature are not so dramatically better than a two-moment scheme as compared to a two-moment and one-moment scheme. That is why to define moments, it's not the whole story. You also need to tune other parameters in such a bulk scheme, that is parameters of a fall speed size relation or a mass size relation. These are also important, and these are not so much depending, so the results are not so much depending if you have two or three moments, but these other parameters are also important, and we think that we could get away with a two-moment scheme, and we don't really need triple moment microphysics, but of course in literature they are published, and I know from Environment Canada they might probably use a triple moment scheme now because Jason Milbrand is working there, a developer of one of these schemes, but I don't know. What we are, for our research, we are really going to another step in microphysics. We have in the ICON an experimental version of a so-called Lagrangian particle model. So there you don't represent hydrometeors by moments, but you represent them by single particles, which are really advected and sedimented around in the model domain. Many particles of different kinds, and they can collide. And so that's an explicit Lagrangian simulation, and that's our research toy model for the next 10 years, I would say. Bin microphysics, of course, I forgot that. Thank you for the hint. Yes, we have colleagues in Israel, Alexander Kain from Hebrew University. They are currently implementing their bin microphysics scheme, which is also capable of forecasting hail and Graupel and all these categories in a sample bin scheme. So there you sample the particle size distribution not with moments, integrals over the size distribution, but you discretize the size distribution function itself in certain bins. And yes, we will get the a bin scheme in ICON from the Israeli colleagues. They are part of the Cosmo consortium where we also apply ICON model now.
Okay, I'm not seeing any more questions, so shall we close this one?
Yeah, we could.
Okay, recording is